Welcome again to Engineers Newsletter Live. I'm Jeannie Harshaw from Trane System and Application Engineering Group, and today we'll discuss SingleZone VAV Systems. This course is approved by the U.S. Green Building Council for 1.5 Green Building Certification Institute continuing education hours toward the LEED Credential Maintenance Program. After attending today's program, LEED professionals should submit their hours to GBCI. Today's program is also registered with the American Institute of Architects Continuing Education System and qualifies for Health, Safety, and Welfare credit. AIA members, please provide your member number to your local host before leaving today's session. And professional engineers, check with your state rules to see if credit for attending today's program can be applied to engineers' continuing education requirements. So, while SingleZone VAV is not a new concept, because of the new requirements in energy codes and greater focus on reducing energy use, we're seeing it used more and more. Today, Trane application engineers John Murphy and Eric Sturm will take us through a discussion of SingleZone VAV systems. We'll start with a discussion of what ASHRAE 90.1 requires in terms of SingleZone VAV control. Then John and Eric will describe how SingleZone VAV systems work, their typical benefits, as well as some challenges and considerations when applying them. And finally, we'll hear from a company who's been using these systems and learn from their experiences. Eric, will you get us started?
One of the reasons for producing a program on this topic is because requirements for SingleZone VAV control were added in the 2010 edition of ASHRAE Standard 90.1, the energy standard for buildings. SingleZone VAV requirements are also included by reference in ASHRAE Standard 189.1 2011, the standard for green buildings. And this is especially significant because the U.S. Department of Energy has mandated that states must update their commercial building code to meet or exceed Standard 90.1 2010 by October 18, 2013. So if not already, these new requirements will soon be impacting many state codes. Before we look at the actual wording of the 90.1 standard, I think it's important to point out that the requirements for SingleZone VAV control are included in the mandatory provisions of Section 6.4. This means that you must comply with these requirements, whether you choose to follow the prescriptive path in Section 6.5 or the energy cost budget in Section 11. In addition, if the project qualifies to use the simplified approach described in Section 6.3, the same requirement for SingleZone VAV control applies. Now, let's look at the requirement from Standard 90.1. This section contains two parts. The first part, addressing systems that use chilled water for cooling, and the second part, which we'll look at next, addresses systems that use direct expansion. Part A addresses air handling units and fan coils with chilled water cooling. The standard requires variable airflow controls if the supply fan is 5 horsepower or larger. For systems in this size range, the supply fan must be controlled by either a 2-speed motor or a variable speed drive. The standard does not require fully variable airflow, as might be achieved with a VFD. 2-speed fan control would be sufficient to meet variable airflow requirements, and the accompanying user's manual clarifies that ECM motors can be used too. The supply fan controls must be able to reduce airflow to at least 1/2 of the airflow delivered at full speed, or down to the volume of outdoor air required to meet ASHRAE Standard 62.1, if that's larger than the 50% threshold. This is meant to prevent the system from underventilating. The Standard 90.1 User's Manual provides further clarification. It states that the term cooling demand refers to the zone-sensible cooling load. So when the zone-sensible cooling load decreases to 50% of the design load, the supply fan controls must have reduced airflow to at least 1/2 of the design airflow. John will dig into this control sequence in a little bit, but first, let's look at the second part of this section. Part B addresses systems that use direct expansion for cooling. For equipment with DX cooling, the standard requires variable airflow controls if cooling capacity is 110,000 BTUs or larger. This equates to just over 9 tons. Note that in an effort to make this simpler to enforce, the size threshold is based on the capacity at the ASHRAE standard rating conditions, not actual capacity at the given application. Standard rating conditions can be found within the established test procedure for specific equipment. As for chilled water equipment, the standard allows DX equipment to use either a 2-speed motor or a variable speed drive on the supply fan. However, the turn-down threshold is less stringent. For DX equipment operating at cooling demands less than or equal to 50%, the supply fan controls need to be able to reduce airflow to 2/3 or less of the full speed airflow. And again, a higher part load is allowed if needed to meet ASHRAE Standard 62. Standard 90.1 is the basis for many states and the International Energy Conservation Code. California has adopted its own energy code. The California Building Standard, also known as Title 24 of the California Code of Regulations, governs construction of new buildings and requires compliance with the California Energy Code. The SingleZone VAV requirements, made effective January 1st, 2012, are similar to those presented in ASHRAE Standard 90.1. Section 144L requires SingleZone VAV control within the prescriptive requirements. The section states that all unitary and air handling units which serve a single zone with an ASHRAE rated cooling capacity of at least 110,000 BTU must be served by variable volume supply fan controlled by either a variable speed drive or a 2-speed motor. At low cooling demand, the supply fan motor must reduce speed to a minimum of 2/3 of design speed. Delivery of ventilation air must be maintained based upon the requirements of Section 121. It's interesting to note that other motor speed reducing technologies are permitted, but must be demonstrated to use less energy to the executive director.
So SingleZone VAV fan control is required, or will likely be soon required by most energy codes. But what is a SingleZone VAV system? Eric's going to answer that question, and then we'll dig into how it is controlled. Eric?
Put simply, SingleZone VAV is any airside system that delivers conditioned air to a single zone with a variable volume supply fan. These may be either 2-speed fans, variable speed drives, ECM motors, or other means to adjust supply airflow when operational conditions change. SingleZone VAV systems can include fan coils, water source heat pumps, rooftop air conditioners, or even air handlers. SingleZone VAV control can really be applied to a wide range of equipment. The traditional constant volume system is designed to serve one zone. Let's have a look at a diagram of this system. This system uses a constant volume supply fan and variable temperature cooling coil. The thermostat compares the zone temperature to a program set point. As needed, the cooling or heating coils are used to condition the supply airstream based upon the signal from the thermostat when the zone temperature deviates from set point. To maintain zone temperature at set point, the cooling coil or heating coil capacity is modulated when the fan operates at constant speed to provide conditioned air to the space. The SingleZone VAV system combines the simplicity of a constant volume system with the energy savings of a VAV system. The SingleZone VAV system uses a variable volume supply fan and cooling and heating coils. There's no need for a VAV box in the supply airstream because the system delivers the proper amount of tempered supply air to meet the load in the zone. A zone temperature sensor signal is used by the system controller to control discharge air temperature, supply fan speed, cooling coil operation, and heating coil operation. The cooling coil is controlled to a single discharge temperature. This is a change from the constant volume system. The space temperature sensor, by way of the system controller, determines the system operation. John's going to show us how a SingleZone VAV system is controlled with an example control sequence.
This chart depicts an example control sequence for a SingleZone VAV system, which uses a variable speed fan. The x-axis is a sensible load in the zone, with design heating load on the far left and design cooling on the far right. When the zone's at design cooling load, this system delivers maximum supply airflow at the design supplier temperature for cooling, 55 degrees for example. As the zone cooling load decreases, supply airflow is reduced as needed to maintain the desired temperature in the zone. This is accomplished by varying the speed of the fan motor. Cooling capacity is then staged or modulated to maintain the supplier temperature at the same design set point. Or if the system has an airside economizer, depending on outdoor conditions, the economizer may provide all or part of the cooling to achieve this temperature. Now eventually the zone cooling load decreases to the point where supply airflow reaches some minimum limit. I'll come back to discuss this limit a little bit later. As the zone cooling load continues to decrease, the fan continues to operate at this minimum airflow. But now the supplier temperature set point is gradually reset upward to avoid overcooling the zone. Depending on the outdoor conditions, as this temperature set point increases, eventually no mechanical cooling is needed to make this temperature, so the compressors are turned off. And even the airside economizer modulates back to bring in only the minimum outdoor airflow required for ventilation. When that happens and the load continues to decrease, the zone temperature begins to drop below the zone's cooling set point into the dead band between cooling and heating set points. Here the fan continues to operate at this minimum airflow with no compressors or heaters operating, and the zone temperature is just allowed to float within that dead band. Now let's consider what happens when the zone eventually requires heating. That is, when the zone temperature drops to its heating set point. The fan continues to operate at minimum airflow, and the supplier temperature set point is reset upward even further. Heating capacity is staged or modulated to maintain this new supplier temperature set point. Now eventually the zone heating load may increase to the point where the supplier temperature reaches some preset maximum limit. I'll circle back to discuss this limit too. As the zone heating load continues to increase, supply airflow is again increased, while heating capacity is staged or modulated to maintain the supplier temperature at this maximum limit. So, at full cooling load, the system delivers design airflow at a cold temperature. But as the zone cooling load decreases, the system first reduces fan airflow until it reaches some minimum limit, and then raises the supplier temperature set point. Same thing when the zone requires heat. At full heating load, the system delivers high airflow at a warm temperature. And as the heating load in the zone decreases, it first reduces supply airflow and then lowers the supplier temperature once the airflow reaches this minimum limit. Now, this is just an example to demonstrate the concept. This control can vary by manufacturer. Plus, there are nuances that depend on whether chilled water or DX is used for cooling, and whether or not the type of heater used can support variable airflow. Okay, let's talk a little bit more about these two limits, the minimum airflow and the maximum supplier temperature for heating. This minimum airflow limit might be determined by how far the VFD or ECM can be turned down. This will be equipment specific and could be due to a number of reasons. It might be to ensure motor reliability, or in the case of DX equipment, for reliability of the refrigeration system. Or in some applications, this limit might need to be high enough to meet some air distribution or ventilation requirement. And remember, as Eric explained, Standard 90.1 requires this minimum airflow to be no higher than 1/2 of design airflow for chilled water equipment, or 2/3 for DX. But if the outdoor airflow required to meet ASHRAE 62 is higher than this minimum threshold, you can use the higher ventilation-related airflow to avoid underventilating the zone. As for the other limit I mentioned, the maximum supplier temperature for heating might also be determined by equipment design. This would most likely be for safety or reliability reasons. In that case, this limit is probably programmed into the controller. Or for some applications, this temperature might be limited to minimize stratification when supplying hot air from overhead diffusers. When both supplier diffusers and return grills are mounted in the ceiling and the supplier is hot, the buoyancy of this hot air will tend to cause some of it to stay up near the ceiling and bypass from the supply diffusers to the return grills. This can cause comfort problems, and as we discussed during our last E&L program in ASHRAE Standard 62, this bypass air impacts ventilation performance and requires bringing in more outdoor air through the system intake. One way to avoid or limit this effect is to deliver the air at a not so hot temperature during heating. In this case, the maximum supply air temperature for heating might be set to 15 degrees above the zone set point. One additional comment. Controlling this type of maximum limit requires a discharge air temperature sensor be included in the equipment. Now, for some type of equipment, the type of heater available may not be able to accommodate variable airflow. In that case, the control sequence may vary airflow during cooling, but then increase to some constant airflow whenever the heater is activated. That is, if the zone temperature drops below its heating set point, the fan ramps up to full speed, and the heater is cycled or staged to warm up the zone. Once the zone temperature is raised back up to that dead band between heating and cooling set points, the heater turns off and the fan again backs down to minimum speed. In addition, as Eric mentioned, Standard 90.1 states that the supply fan can use either a variable speed or a two-speed motor. The most common implementation of a two-speed motor is probably a DX unit that has either two compressors or one two-stage compressor. This allows the equipment to be used with a conventional thermostat with Cool 1, Cool 2 control. This chart depicts an example control sequence when using a two-speed fan. Again, this can vary by manufacturer and product design, so this is just an example. When the thermostat calls for both stages of cooling, the supply fan operates at high speed with both compressors on. When only one stage of cooling is needed, the fan turns down to low speed with only one compressor operating. Then when the thermostat calls for no cooling, the fan continues to operate at this low speed, but both compressors are shut off. So basically, fan speed follows the compressors as they're turned on and off. If both compressors are on, the fan's at high speed. If only one compressor is on, or if they're both off, it's at low speed. Finally, if the thermostat calls for heat, the fan operates at high speed and the heater turns on. When the zone warms up, the thermostat shuts off the heater and the fan returns to operate at this low speed. Now, like with variable speed fan control, the minimum airflow at the low fan speed might be determined by equipment design for safety or reliability reasons. And again, Standard 90.1 requires this minimum airflow to be no higher than 2/3 of design airflow for DX equipment, or 1/2 of design airflow if it's chilled water. So that's how these systems operate. Next, Eric's going to discuss some of the applications where these systems are typically used.
SingleZone VAV is not a new concept, but due to the aforementioned requirements in energy codes and an overall heightened attention to reducing energy use, we're seeing it used more and more. Traditionally, SingleZone VAV has been used for larger, densely occupied zones that have variable cooling loads. Common examples include gymnasiums, cafeterias, lecture halls, auditoriums, or large meeting rooms, churches, and arenas. However, because of increased focus on reducing energy, we're also starting to see these systems used more in K-12 classrooms, retail stores, dormitories, and even offices. Since SingleZone VAV was traditionally used in those larger type zones, it's been available primarily in large air handling units and large package rooftop equipment. This type of equipment has been available for years with variable speed fans and cooling and heating that can be staged or modulated to control discharge air temperature. However, as SingleZone VAV has become more popular for the smaller zones found in schools, stores, and offices, we're starting to see this functionality offered in smaller equipment. Equipment like small package rooftops and DX splits, fan coils, and classroom unit ventilators, and even water source heat pumps, which we discussed in our E&L program last summer. Another aspect of air system control involves ensuring proper zone ventilation at all operating conditions. With a constant speed fan, ensuring proper ventilation is done by setting the position of the outdoor air damper during startup and balancing. Kind of a set it and forget it approach. But more and more, SingleZone VAV is being used instead of traditional constant volume systems. With a variable speed fan, designers can no longer simply set it and forget it. John's going to explain.
To demonstrate, let's look at this diagram of a simple SingleZone VAV system. This accompanying chart depicts the static pressure as air moves through the various components of the system. Positive pressure above this dashed line and negative pressure below it. Now the supply fan must create a high enough pressure at its discharge to overcome the pressure losses associated with pushing the air through the supply ductwork and diffusers and into the zone. In addition, the fan must create a low enough pressure at its inlet to overcome pressure losses associated with drawing the air out of the zone and through the return air path, which might include a return grill, ceiling plenum, and maybe some ductwork. And then to draw the air through the return air damper, filters, and coils inside the air handler or rooftop unit. For this particular system, this mixing box is where outdoor air mixes with the recirculated air. Due to the pressure drop through the return air path, the static pressure in this mixing box is negative. That is, it's lower than the pressure outside the building. This causes outdoor air to be drawn into this mixing box. The return air damper is adjusted so that the pressure in this mixing box is low enough to ensure that the desired CFM of outdoor air enters through this outdoor air damper. Now let's see what happens as supply airflow decreases during part load operation. Pushing less air through the supply ductwork and diffusers results in less pressure loss. So the fan doesn't have to generate as high a pressure at the fan discharge. In this same manner, moving less air through the return air path also results in less pressure loss. This causes the static pressure inside the mixing box here to increase. That is, it's not as negative as it was at design airflow. The static pressure inside this box has a direct effect on how much outdoor air enters the system. If this damper remains set at a fixed position, the CFM of outdoor air entering through the damper will decrease because the pressure inside this mixing box is not as negative. The result is that outdoor airflow will decrease as supply airflow is reduced. So to ensure that the same CFM of outdoor air enters the system, you need to open this damper further when supply airflow is reduced. This requires designing and programming a control sequence that was not necessary with a traditional constant volume system. Now, while there are others, I'll describe a few approaches that might be used to address this issue and ensure proper ventilation in a SingleZone VAV system. I'll start with those systems that use a two-speed fan. This one's pretty simple in that you just need two position set points to control the outdoor air damper. Here again is the example control sequence for a two-speed fan system. When the fan is operated at high speed, the outdoor air damper position is set to bring in the quantity of outdoor air required by code. Then when the controller switches to operate the fan at low speed, the damper is adjusted to a more open position in order to bring in the same CFM of outdoor air. When the heater is activated and the fan is again operating at high speed, the damper position changes back to the original setting. So fan speed and damper position are controlled together. Whenever the fan runs at low speed, the damper is open to this further open position set point. Of course, these are minimum position set points. If the system uses an airside economizer, the damper may be opened further when conditions are suitable for economizing. Next, for systems that use a variable speed fan, a relatively inexpensive solution could be to modulate the position of the outdoor air damper in proportion to the changing fan speed. I'll demonstrate this with this chart. Supply fan speeds on the x-axis from minimum speed to maximum speed, and damper position is on the y-axis from fully closed to fully open up here. First, with the system operating at the design supply airflow and maximum fan speed, the outdoor damper is positioned to a set point that brings in the quantity of outdoor air required by code. Then, when the system operating at minimum airflow, the damper is adjusted to this more open position in order to bring in the same CFM of outdoor air. During system operation, the controller modulates the position of this outdoor air damper in proportion to the change in supply airflow, which is determined from the signal sent to the variable speed drive on the fan. So the controller first adjusts fan speed, like I described in the variable speed fan control sequence. Then, using that current speed, the outdoor air damper position is modulated according to this proportional relationship, opening further as fan speed is reduced. Again, this is the minimum damper position. It may be opened further when conditions are suitable for economizing. Now, this method is not perfectly accurate over the entire range of airflows, since damper performance is nonlinear, and it doesn't account for outside influences like wind or stack effect. So it does result in some overventilation here in the middle of this range, but much less overventilation than if a fixed position damper was used. That's because standard 62.1 requires that a system maintain the required minimum outdoor airflow under any load condition. And it clarifies that if a variable airflow system uses a fixed position outdoor air damper, you need to be sure that it complies at the minimum system airflow. This means you need to fix the damper position up here so that you bring in the minimum required outdoor airflow when the fan is operating at minimum speed. Of course, this results in overventilating at all these other fan speeds. So a proportional damper control strategy results in significantly less overventilation than fixing the damper position up here for worst case. Plus, it's relatively inexpensive, so it's used in a lot of smaller single-zone VAV applications. I mentioned that there is some inaccuracy since damper performance is nonlinear. One way to minimize this inaccuracy is to add a third damper position set point at some intermediate airflow. This ensures proper ventilation at this intermediate speed and minimizes any overventilation by shrinking the ranges between these set points. Another method for controlling ventilation could be to actually measure the outdoor airflow and control it directly. This is typically accomplished by using a flow measuring device in the outdoor airstream, such as an airflow measurement station or a flow measuring damper. This method is more accurate over the range of airflows and can respond to pressure fluctuations caused by wind or stack effect. This direct control reduces the energy use associated with overventilation and has the added benefit of providing a means to document the outdoor airflow brought into the system over time. However, outdoor airflow measurement does increase the cost of the system, so it's probably more likely to be used in larger systems. These three approaches make sense for a piece of equipment that has a mixing box and an outdoor air damper, such as a packaged rooftop, air handling unit, or a classroom unit ventilator. But what about fan coils or water source heat pumps? Many models of that type of equipment just have a single inlet opening, no mixing box or outdoor damper. Ventilation is typically provided by a dedicated outdoor air system. In a lot of these applications, the dedicated outdoor system delivers the conditioned outdoor air to the inlet side of each local heat pump or fan coil. For a horizontal style unit, the air might be ducted to the discharge into the open plenum near the unit's intake. For a vertical style unit, it might be ducted to a closet where the unit's installed. In either case, the outdoor air mixes with recirculated air in the plenum or in the closet before being drawn in to the local heat pump or fan coil. Just like I described earlier, if this local unit has a 2-speed or a variable speed fan, the static pressure at the inlet is not as negative when fan speed is reduced. So again, outdoor airflow will decrease as supply airflow is reduced. An added challenge is that the outdoor air is delivered to this point by a separate fan, and the pressure in this ductwork is influenced by the changing operation of all the local fans served by this ventilation system. With this configuration, to ensure you get the required outdoor airflow, you should add a pressure-independent VAV box to the ventilation duct for each zone. Then as the fan speed changes, this damper modulates to maintain the same CFM of outdoor air regardless of fan speed. Now a better choice would be to deliver the conditioned outdoor air directly to each zone. In this case, the local heat pump or fan coil conditions only recirculated air. Since outdoor air is not distributed through the local fan, that fan can operate with a 2-speed or a variable speed motor without impacting how much outdoor air is delivered. This direct-to-zone approach also affords the opportunity to deliver this outdoor air at a cold temperature, rather than reheated to neutral. This has several installed cost and energy-saving benefits. I discussed these benefits in detail during a 2012 E&L program on water source heat pump systems. It's listed in your bibliography if you want to learn more. So when a dedicated outdoor air system is used, consider delivering the conditioned outdoor air directly to each zone, rather than to the inlet of the fan coils or heat pumps.
Because the supply fan speed changes, ensuring proper ventilation in a single-zone VAV system is probably more challenging than for a traditional constant volume system. So be sure to give it more consideration when designing the system and its control. These strategies John mentioned are a good start. Before leaving the subject of ventilation, single-zone VAV systems are often used for densely occupied zones with varying population. This typically makes them good candidates for using CO2-based demand control ventilation.
Carbon dioxide is produced by the occupants and diluted by outdoor air. So the difference between indoor and outdoor CO2 levels can be used as an indicator of the outdoor airflow rate being delivered to the zone. With this approach, a sensor measures the concentration of CO2 in the zone. This concentration is used by the controller to reset the outdoor airflow as population changes. This saves energy by not overventilating the zone during periods of partial occupancy. However, while ASHRAE Standard 62 allows the use of demand control ventilation, it also includes a few requirements to make it work. For example, the controls cannot be allowed to reduce outdoor airflow any lower than the building component of the ventilation rate. This is defined by the CFM per square foot rate, or R sub A, that's listed in the standard for that type of zone. So while the CFM per person component can be varied, you cannot go any lower than the CFM per square foot component. Section 8 clarifies that this applies whenever that zone is expected to be occupied. That is, the standard is not requiring you to deliver this building component of the ventilation rate 24 hours a day, 7 days a week. Rather, it only requires it during the normally scheduled occupied period. So when implementing demand control ventilation, Standard 62 does not allow you to go below a certain CFM. The challenge is this: because this mixing box pressure varies as supply airflow changes, you need to make some provision to prevent outdoor airflow from dropping below this minimum CFM threshold. So even when using a CO2 sensor for demand control, it must be combined with either proportional control or a flow measuring outdoor air damper. Now the Standard 62.1 User's Manual describes a proportional control sequence that can be used to implement demand control ventilation in a single zone system. To explain it, let's use an example 1,000 square foot lecture classroom with a peak population of 65 occupants and a CO2 generation rate that's typical for people doing light office work. The first step of the process is to calculate the outdoor airflow required at both peak population and with 0 people. Using the rates required by ASHRAE 62 for this type of space, our example classroom needs 550 CFM of outdoor air when all 65 people are present. But it only needs 60 CFM when the zone is unoccupied, but the ventilation system is still operating. The second step is to calculate the CO2 concentrations using the steady state equation found in the standard. For our example, assuming an outdoor concentration of 350 parts per million, the indoor concentration of CO2 that corresponds to peak population is 1,600 parts per million. And the concentration at zero population is 350. These values define the endpoints for a simple proportional control sequence. When the space CO2 concentration equals 1,600 parts per million or higher, the outdoor air damper modulates to bring in the design outdoor airflow of 550 CFM. When the concentration is 350 or less, the damper modulates to bring in 60 CFM, which is the building component of the ventilation rate. And when the CO2 concentration is between these two limits, the controller modulates the outdoor air damper proportionally between 60 and 550 CFM. Now, if the system has a flow measuring damper, it just controls to this new CFM set point. But if proportional damper control is being used, it takes a bit more engineering of the controller.
Now that we've covered how SingleZone VAV systems work, let's look at some of the benefits of using them. Compared to a constant volume system, typical benefits of SingleZone VAV include lower energy use, improved dehumidification at part load, and less fan-generated noise at reduced speeds. Eric, can you address the energy savings?
Sure. We now know that SingleZone VAV systems are suitable for spaces that have varied cooling load profiles. These reduced cooling loads present opportunities for part load energy savings with respect to the supply fan, exhaust or relief fan, and compressors. As the cooling load decreases, the fan motor can reduce its speed and airflow. In addition to reduced electrical demand, the compressors respond by cycling, reducing speed, or any other unloading method. This also allows for additional energy savings compared to a traditional constant volume system. Validating potential energy savings with an energy modeling program, such as Trane 700, can be considered. Simulating SingleZone VAV systems within Trace is quite simple. First, select the SingleZone variable air volume system from the system type list in Create Systems. Next, you can configure economizer or heat recovery components on the options screen. Skipping forward to the temperature and humidity screen, you can specify coil discharge air temperatures or supply air temperatures at the diffuser. Heating supply air temperatures can also be input. Finally, on the fan screen, you can specify your system fans, including supply and exhaust. You're able to define the full load energy rates and fan efficiency information for each. Selecting the cooling equipment is also quite simple. Several reference SingleZone VAV plants based upon existing products have been added to the standard library for convenience. On the configuration screen of Create Plants, you can create new cooling plants and assign a category of equipment to each. Further refinements for each cooling plant can be made on the Cooling Equipment tab of Create Plants. Here, you can input your heat rejection equipment, cooling capacity, and energy rate. To illustrate potential benefits of a SingleZone VAV system, we used Trace to run several simulations. We started with a small elementary school and focused on several spaces that would each be served by a SingleZone VAV rooftop unit. To see variations related to climate, we selected 3 locations for simulation: Atlanta, Georgia, Minneapolis, Minnesota, and St. Louis, Missouri. Each simulation uses an ASHRAE standard 90.1 2007 baseline model for comparison. We then changed the airside system to a SingleZone VAV and made incremental changes. First, 2-speed fans were used, and finally, variable speed drives were used. We did not alter the envelope or internal loads. The only changes from alternative to alternative are within the airside systems. The simulated elementary school is a single-story building and suitable for rooftop units. We focused the analysis on 2 classrooms, the cafeteria, and the gymnasium. Internal load and population density information was selected using the Advanced Energy Design Guide for K-12 schools. Let's start looking at output data from the simulations. This analysis compares the HVAC energy expenditure only. The energy consumption is expressed as a percentage with the standard 90.1 model being a baseline. Each city is represented with a baseline model marked in blue. The yellow bars show the system energy usage for single-zone VAV systems with two-speed fans. In this instance, the two-speed fans operate at design airflow when the system is heating. The results show potential to save energy by employing single-zone VAV systems even with two-speed fans. Remember that two-speed fans are the minimum defined by standard 90.1. The energy reduction for Minneapolis is more than one might expect when comparing two-speed fans with constant volume design heating airflow. Despite the winds of Thor blowing cold, there are mostly cooling loads because of the high internal loads of the simulated spaces. In buildings with high heating loads, we would expect more fan power consumption and less overall HVAC energy savings. The next alternative, variable speed fans, uses VFDs to control the fan motor speed. By simulating the same buildings with variable speed fans, system energy consumption is reduced even further, by several percent for each location. This analysis assumes variable speed airflow for both cooling and heating. The space types simulated rarely operate at design airflow, which allows for significant run hours at part load. Additional energy conservation measures could be added and evaluated to further reduce energy consumption. Comparative enthalpy economizers can be used. Demand control ventilation could be used and in some instances may be required by code. Optimum start and stop controls could be added to enhance comfort and energy usage. These simulations assumed minimally compliant rooftop equipment. That is, the equipment used standard 90.1 efficiency rates. If you're replacing existing equipment, the refrigeration system efficiency may be better than the existing equipment. During our analysis, we did notice that compressor energy increased. Remember that single-zone VAV systems operate with a fixed discharge air temperature that is lower than the discharge air temperature of a constant volume system when operating at part load conditions. The VAV system continues to deliver cool, dry air at part load conditions. This colder, drier discharge temperature has dehumidification benefits and energy consumption drawbacks, but the meter is on the building and the fan energy savings offset the additional compressor energy many times over. John's going to demonstrate with an example of part load dehumidification.
To demonstrate the dehumidification benefit, here's an example system serving a single classroom in Jacksonville, Florida. At the cooling design conditions for this location, this system mixes 450 CFM of outdoor air with 1,050 CFM of air recirculated from the zone. Then it delivers this 1,500 CFM of supply air to the classroom. At this full load condition, the system cools the air to about 55 degrees to offset the sensible cooling load in the zone, maintaining zone temperature at the desired set point of 74 degrees. Plotting this system on the psychrometric chart, the outdoor air mixes with the recirculated air. Then this mixed air gets cooled and dehumidified to about 55 degrees. This cool, dry supply air enters the space where it absorbs sensible heat and moisture. So for this example, the resulting relative humidity in the classroom is about 52% at design conditions. Now let's look at part load. This is the peak dew point condition for Jacksonville, when it's not as hot outside, but it's more humid. This system, with a constant speed fan, continues to supply air at a constant volume, 1,500 CFM in this case. Meanwhile, as the sensible cooling load in the zone decreases, the compressor cycles on and off, resulting in warmer air delivered to the zone, 63 degrees for this example load condition. Now, although delivering this warmer air prevents overcooling and maintains the zone temperature at set point, the cycling compressor results in a warmer average coil temperature and less moisture removed. This 63-degree air has not been dehumidified as much as if it was cooled down to 55 degrees. This warmer, wetter supply air causes the zone humidity level to rise. At this part load condition, the resulting relative humidity is 67% compared to 52% at full load. Now let's consider the same example, but using a system with a variable speed fan. When the sensible cooling load in the zone decreases, this system responds by first reducing airflow delivered to the zone while maintaining a constant supply air temperature. At this same part load condition, supply air flow is reduced from 1500 to 900 CFM, while still delivering the air at 55 degrees. Reducing the airflow allows the system to continue supplying the air at a cool temperature, which means it's also dry. The coil removes more moisture, improving dehumidification performance. At this part load condition, because the supply air is still cool and dry, the relative humidity in the classroom rises to only 57% with the variable speed fan compared to 67% with the constant speed fan. A pretty significant improvement. Now in this comparison, for the variable speed fan system, the load in the cooling coil is 4 tons and the fan moves 900 CFM. So achieving this lower humidity level requires a bit more compressor energy while benefiting from much lower fan energy. Here's another challenging condition, a mild rainy day. Now I'm not going to talk through this chart, but I did include it in your handouts. Similar results here. The variable speed fan results in much better dehumidification, 60% RH compared to 73% with a constant speed fan. Now another method for improving part load dehumidification could be to add hot gas reheat. In order to limit space humidity to 60%, a constant volume system will overcool the air to dehumidify it and then reheat it to prevent overcooling the zone. This requires more compressor energy along with more fan energy. For many applications, the variable speed fan may do a good enough job of limiting indoor humidity levels, so you may not need to equip the system with any other dehumidification enhancements like hot gas reheat. But if a project requires lower space humidity levels than the SingleZone VAV system can achieve, some types of equipment can be equipped with hot gas reheat also. In that case, the variable speed fan will likely limit humidity most of the time, but the reheat can kick in if it's ever needed. In the case of fan coils or water source heat pumps, a more efficient approach would typically be to use a dedicated outdoor air system to dehumidify the outdoor air centrally, rather than equip each local unit with reheat.
Let's return to our example energy analysis and look at some additional output data. John gave us a nice overview of SingleZone VAV's ability to dehumidify spaces. Trace has a space humidity output report called the Building Humidity Profiles. We can use this report along with the Trace output graphing tool to verify the space relative humidity levels. First, let's look at the output report. This report allows us to review the space humidity values throughout the simulation. Relative humidity for each space is reported for all hours of the simulation and all occupied hours. Let's take a closer look at the occupied hours for a constant volume system versus a SingleZone VAV system. Here are the results. The report provides the maximum and minimum relative humidity values for each space at the time of occurrence. The center section shows us the number of hours within each 5% bin. A large quantity of hours on the left side would represent many occupied hours with high relative humidity. As a general rule of thumb, ASHRAE Standard 55 tells us that high relative humidity levels combined with low metabolic activity results in occupant discomfort. For the classrooms, these occupied hours of high relative humidity may be poor for the students and faculty. Next, let's look at the same table for the SingleZone VAV system. Based upon the part load dehumidification aspect of a VAV system, we should see lower relative humidity numbers. Looking at the center section, where the number of hours for 5% bins are reported, we can see a significant change. There are fewer occupied hours with high relative humidity values, say greater than 62%. This should translate into a more comfortable space for the occupants and a reduced likelihood of microbial growth. The Building Humidity Profiles report is a convenient way to review the space relative humidity from the simulation. The Graph Profiles and Energy program, sometimes called the Visualizer, is another tool that can be used. It can be configured to show many different variables from the simulation, both in a tabular and graphical format. In this custom configuration, I've plotted the maximum hourly relative humidity for a specific day when the school is occupied. The horizontal axis shows the hours of the day. The vertical axis on the left shows the relative humidity expressed as a decimal, and the vertical axis on the right shows dry bulb temperature in Fahrenheit. The green line near the bottom of the chart featuring open boxes is the space relative humidity for the modeled classroom from the constant volume single-zone alternative in September. Maximum space dry bulb temperature is represented as the red line featuring open triangles. After the students arrive at hour 7, the space relative humidity peaks and fluctuates throughout the occupied period. Space temperature falls from the unoccupied set point to the occupied set point, 75 degrees Fahrenheit, once occupancy begins. Next, let's look at the same chart for a single-zone VAV system. With this system, the relative humidity does spike as occupancy begins in the morning, but the peak never reaches the same level of the constant volume system for the same classroom. For this system, the relative humidity remains lower than the constant volume system. The data can be copied and pasted or exported to your favorite spreadsheet tool. In addition to energy savings and improved dehumidification, another benefit of single-zone VAV systems can be the part-load fan characteristics related to acoustics. Air distribution equipment, including fans, ductwork, and diffusers, have a significant impact on background sound within conditioned spaces. Most sound generated by a fan results from high-velocity air passing through the fan wheel and housing. As the fan motor speed decreases, the sound level will decrease as well. This analysis shows a sample airfoil fan. The primary octave bands are shown across the horizontal axis, and the sound power level, measured in decibels, is shown in the vertical axis. As the fan operates at design airflow, sound is generated at each octave band. When the fan begins to turn down to 90% of design airflow, the sound power decreases. As the fan turns down further, the sound levels will continue to decrease, shown here in 10% intervals. The sound generated is based upon the type of fan, flow rate, total pressure, fan efficiency, drive system, and discharge.
So, typical benefits of a single-zone VAV system include lower energy use, improved dehumidification at part load, and less fan-generated noise at reduced speeds. But in order to realize these benefits, the specific application must be well suited for using single-zone VAV. So next, the guys will discuss some of the challenges or considerations that you need to be aware of when applying this type of system. Eric?
First, the loads throughout the zone need to be fairly uniform. This is a single-zone system responding to a single temperature sensor, so it doesn't have the capability to satisfy simultaneous heating and cooling requirements. If the loads throughout a large zone are not fairly uniform, it may result in undesirable temperature variations in some areas of the zone that are further away from the temperature sensor. This is really no different than for a single-zone constant volume system, where the same challenge can occur in larger zones. Second, design the air distribution system to accommodate variable supply airflow. Use diffusers that will provide proper air distribution at reduced airflows. Diffusers that are appropriate for conventional VAV systems are probably best suited. And, in general, keep the duct runs as short and symmetric as possible. Systems with longer or asymmetric duct runs are more susceptible to unequal airflows between diffusers as the supply fan modulates. Here's an example of symmetric ductwork. The path from the supply fan to each of the 4 diffusers is about the same, so pressure losses of the 4 paths are about equal. This is good practice for any air system. In contrast, here's an example of asymmetric ductwork. The path from the supply fan to the lower 2 diffusers is shorter and straighter than the path to the upper diffusers. In this case, balancing dampers can be installed to add pressure loss to the 2 closer diffusers and force more air down the longer paths. Once balanced, if the fan operates at a constant speed, the distribution of air to these 4 diffusers remains essentially the same during operation. But with a variable speed fan, the pressure losses through the longer and shorter paths do not necessarily remain proportional as the fan speed changes. For example, when the fan is operating at a design airflow of 2,000 CFM, the system is balanced to deliver 500 CFM to each of the 4 diffusers. But when the fan speed reduces to deliver 1200 CFM, you probably won't get exactly 300 CFM from each diffuser. More air will come out of the diffusers closer to the fan, and less will come out of the diffusers with the longer duct runs. The amount of variation depends on many factors, including the relative duct lengths and the number, type, and proximity of the duct fittings, so it's not easily quantified. So keeping the duct runs as short and symmetric as possible is general good guidance. With that said though, asymmetric ductwork is not necessarily a showstopper for using single-zone VAV. It just means that the zone is more likely to experience unequal airflows between diffusers as the fan speed changes. The next one we already discussed in detail. You need to provide some means to ensure proper ventilation to the zone as supply airflow changes. John described a few possible approaches earlier.
For some types of equipment, two-position or proportional damper control might be used. Larger systems may use actual airflow measurement. Or when a dedicated outdoor air system is used, consider delivering the conditioned outdoor air directly to each zone, rather than to the inlet of the local equipment. And if you do implement demand control ventilation, don't overlook that you probably need to provide some method to reduce exhaust airflow too. This prevents negative building pressure when demand control reduces the intake airflow. Likewise, if a zone has some type of minimum exhaust requirement, like a restroom, kitchen, or locker room, demand control should not be allowed to reduce the intake airflow any lower than the required exhaust, unless the zone receives makeup air from some other source.
The next consideration is related to system operation during heating. ASHRAE 90.1 addresses single-zone VAV during cooling operation. But if you also want to allow variable airflow during heating operation, you probably need to use some type of modulating heat source.
I showed this example control sequence earlier. The right-hand side of the chart shows variable speed operation when cooling, while the left-hand side shows variable speed operation when heating. To enable variable airflow when heating, you'll likely need to use equipment with either a modulating gas heater or a hot water heating coil. Otherwise, if the equipment has on-off gas or electric heat, the manufacturer may require the unit to operate at full airflow whenever the heater is activated. So you want to check with the manufacturer when specifying or purchasing single-zone VAV equipment.
The final consideration we'll discuss is that a system with variable speed fan control will require a zone temperature sensor rather than a thermostat. John mentioned earlier that a conventional thermostat with Cool 1, Cool 2 control can be used for two-speed fan control, but not for variable speed control. For a new system, this is probably just something you want to be aware of when specifying or purchasing. But it can create a challenge if you're replacing an older piece of equipment with a new variable speed fan unit. If that old unit was controlled by a conventional thermostat, it will likely need to be replaced with a zone sensor. Thankfully, wireless sensing technology makes this a whole lot easier, especially for those projects where pulling wires would be difficult.
So far, we've discussed how single-zone VAV systems operate, their benefits and challenges, and recent changes to Standard 90.1. One potential energy-saving opportunity in existing buildings could be to replace existing single-zone constant volume units with either two-speed or variable speed units. So to finish up the CNL, we thought that you might be interested to hear about the real-life experiences of one company who has been doing just that.
Walgreens is the nation's largest drugstore chain, with sales of over $70 billion and more than 240,000 employees. The company is also committed to reducing costs and its carbon footprint through sustainable practices. A few weeks ago, we invited Hakeem Yalla from Walgreens to join me in the studio, and I asked him to share about their experiences with replacing existing constant volume rooftop units with new single-zone VAV units in their stores. Joining Hakeem was Nirmal Sakri, a national accounts team leader in Trane's Chicago office. So Hakeem, before getting into today's subject, can you tell me a little bit about Walgreens' sustainability program and efforts in general?
A few years ago, we were tasked to we were basically challenged to try to come up with some ideas or some initiatives that what we call the 3P approach, like that save us money, invest on people, profit, and planet. So we had several initiatives that we started a few years ago. I'm going to be very brief and try to list a few of them, but then I'll mention the most important that we concentrate in most of the time, or mostly. We have, in our stores, at the beginning we have open door coolers, what we call the cooler door retrofit, where we added closed up the doors, like we added some doors to save energy. We have the LED light, we will replace different, like just simple lamp that with the LED lamps. Mm-hmm. We had, by the way, we're trying some solar stores, we're trying some electrical vehicle charging station. And one of the most important initiatives that this is I think the third year that we're doing, basically we replaced almost 1,400 locations so far. We did it at the rate of about 500 locations a year is the rooftop unit replacement. And I remember in 2010 when we were tasked to start the initiatives, we were preparing a business case to get the approval for the funds. It was very challenging. So one of the, my partner and friends, Nirmal, he has been a huge help into making it happen, through the details, go through what kind of unit we replace, what kind of unit we have, and what are the criteria to qualify a store for replacement. Mm-hmm. And I think he can go through more details from Trane side, what you guys contributed on that.
Yeah, John, we started the program in 2010. The challenge by Walgreens to all of their partners, be it HVAC or, to Akeem's point, cooler doors or whatever it might be, has been to make sure that the best product is getting in place as quickly as possible. Walgreens took a look at the footprint they have from about 2008 till about 2010. Analyses were done to look at what a return on investment would be if Walgreens invested capital into the existing footprint. Mm-hmm. And in 2010 is the first year that Walgreens went forward with it. And the return that they saw was they were happy with it. And it pushed the program forward from 2010 all the way through this year, as Akeem said.
Okay. So I understand part of that has been, kind of tying into today's topic, has been to replace constant volume rooftop units. I think it was 2-speed fan units you've talked to me about. Can you tell me more about that application? I assume it's in stores, which most of us are probably familiar with. Is that the building type and the age of equipment that you're replacing?
We were refining our criteria as we gone along with learning the process and becoming basically the leader on the retail business on this. Mm-hmm. What we did in the beginning, we just went to the age, because first of all, it's not just energy. We went to the proactive approach. For example, and you guys are familiar, if you have an emergency, you have a breakdown, you're going to have a contractor come in and install the units, try to mobilize the site. It's costly. Mm-hmm. So we went to the proactive approach, replacing before failure. So okay. It kills the downtime. The downtime, basically we eliminate the downtime. We reduce the maintenance cost, and you have a brand new unit. Okay. So at the beginning, the criteria, we said, okay, every store that is 13 years or older, just to start somewhere, 13 years or older, we're going to put it on the list, and we're going to go through different areas and concentrate on the highest energy cost, the highest utility rebates. And our engineering team, working with Nirmal, basically, he came up with the idea. He said, hey guys, most of the stores are over-designed because the tonnage was much higher, so which means increase the running time. And what we did, we tried to review the design and the load, the CFM, and by the way, our retail business is about 14,000 square foot in average. Mm-hmm. So we found out that we can reduce an average about 5 tons per store. That's a huge saving, in addition to energy efficient unit, in addition to a brand new unit that you're going to balance very well. Mm-hmm. And the saving was amazing.
Okay. So currently I understand you're using units with 2-speed fan control. Any looking at the variable speed of the SingleZone VAV kind of concept? Have you been considering that at all too?
In 2010, to Akeem's point, the idea and the focus was, as you said, it's starting somewhere, right? Mm-hmm. So before that, Walgreens' focus was really making sure that they were expanding their footprint. In 2010, they got to a point of saying, okay, we've got this, 7,500, 7,600 sites across the country, including Puerto Rico. It's probably a good idea for us to look back and invest some money back into our existing footprint versus making sure that we're expanding at the rate that we have been. So 2010 was that 13-year-old kind of benchmark that Walgreens looked at and said, stores that are older than that or equipment that's older than that, let's make sure we look at those stores first. In 2011, it jumped to more of a focus in saying, okay, we have a dollar figure that we're looking to invest into our footprint with respect to HVAC. What is going to give us the greatest return? And so we looked and said, okay, we've got a number of different aspects that are involved with this. We have age of equipment. We have, I guess you could call it the grade of the equipment as well.
Yes.
Right? So how is functioning, how many issues they've had over the course of the years. And Walgreens has done a very good job of keeping track of that equipment as they were self-servicing up till about a year and a half ago or so. So from there, other ideas or facets were put in place. The addition of the utility rebates and where the opportunities existed there. There's a potential right now that they're looking at currently for 2013 is, can EPACT actually play a part or provide benefit to Walgreens? Sure. And then from there, to Akeem's point, putting in high efficiency equipment, that was the baseline. Walgreens has always put in high efficiency equipment. Now what can they look at to say, okay, we've got a variable store. We can't look at our store and say that it's going to be 0 tons or 45 tons. We have people coming in all the time. So they took measurements of when their highest traffic rates are within the year, or within the day, I should say, and within the year. And then they decided that having variable capability units on their stores is probably going to be a better return for them, because while you have that existing footprint reduced 5 tons, they're going to they take it from 40 tons, let's say, down to 30, 35, 36 tons, something like that on average. But those 36 tons are going to function in a variable capacity. And so dual stage was the first step that Walgreens took. It said, this makes the most sense for us. We can see for the larger units, those larger units are now not always running full bore. Yeah. So it's going to make more sense for us to look and say, let's provide that variable capability to see the returns on that. And then do you remember what you guys have seen energy return-wise with the dual stage units around about?
The numbers vary. For example, the highest was in Puerto Rico because we paid there 25 kilowatt hour, 25 cents kilowatt hour. Oh, wow. Then the second highest was the return because of cooling time that was running in Florida. And this is where we concentrated most of the stores. Okay. And I think, but to elaborate a little bit, we came up with the improvement that we did through the years. We didn't concentrate only on the age of the store or the design or the load, or we had, actually he was a big part of it. We established kind of a site survey sheet where you grade the units. We came up with the criteria, say, okay, this unit is 5-6 years old. It's a checklist where you can, then at the end you come up with a score. You say, okay, if this passed 15 points, we're going to replace it. If this with 13, we can take a little bit, of course, we have with respect of energy efficiency. Yeah. And that has been, first of all, it was more saving to our budget, because the more money we save, the more location we can complete. And this has been basically we break it to science compared to 2010 to now.
Mm-hmm. So your considerations when you're making these decisions on whether to upgrade these high efficiency equipment, you talked about energy savings.
Yes.
Is probably one of the drivers, it sounds like. Other benefits that you were hoping to get from these 2-speed units?
Yes, sir. Yeah, there was, to Akeem's point about the focus in Puerto Rico with the high utility rates, Florida, areas like that, Walgreens has been seeing for years a lot of issues with humidity control. They have put in place hot gas reheat in the past. They looked and said it's probably better for us from a direct perspective to lower that airflow and take advantage of that dual stage motor and not have to necessarily utilize hot gas reheat. So Florida was the biggest area, I think, that we saw the greatest return with respect to direct humidity control. And the associated savings that Walgreens was looking at was, on average, from a predicted perspective, we rounded about somewhere between 20 and 30% was the expectation. And I want to say it lined up pretty close to that as far as what they saw.
It was basically, I didn't forget, I'm sorry, to answer his question when he asked me, it's about 35 to 37%.
35% savings on,
yes,
on average on the stores.
Yes.
By upgrading as well. That's pretty good.
Yeah, it was, and it was the results were so good that we were requested because of the percent of depreciation with the economical incentives that we had 100%, this year is 50%. In order to take advantage of the saving, we were requested to, if we can do by the end of calendar year, because Walgreens fiscal year is August 31st, by the end of the calendar, if we can put on the list like about 1,000 locations this year.
Oh, wow, okay. That's going to make you feel pretty good.
Hopefully, yeah.
Interest from the others. In terms of the other aspects of it, like I'm assuming when you went into this business case, you took into account the costs. What's it going to take to actually replace these units? Any surprises there in terms of are kind of your estimated how much work it would take or time or downtime kind of playing out, or are there any things that you learned in there that you were surprised about?
Actually, the biggest, what we call the icing on the cake, the additional saving that we didn't even see at the beginning was, of course, we put it down into the business case, but it was for them hard to believe because I'm the business of maintenance. But for those, it was hard to believe until we showed the result in 2010 and 11. The numbers start coming back from the new stores. What we did, of course, for the stores, you replace a compressor basically almost, including labor, is a third of the price of the unit. You have a heat exchanger, you're going to have the same problem. The reason we tackle, the older stores, because the warranty is expired, so anything that you may, you have to rent a crane, you have to have contractor come in overnight, you have a breakdown timing, so all involved. So when they start monitoring the new locations, first of all, we have the warranty. We renew the warranty on. We have just Walgreens. I don't know what you guys do with the other retailers. We have a 5 years warranty in compressors, 10 to 15 years in heat exchangers, and the breakdown was basically eliminated about 95% on the units, except warranty issues. It did happen because we did. I think the failure or the install failure or the failure of the unit among 1,400 locations was about 5%. So you can't even evaluate or compare to what it used to be and now. So the older locations, they have seen the saving in energy. They have seen the initiative was driven by the saving in energy. The additional saving was on maintenance, was less breakdown, was a better running time for the stores, and then the soft benefit, which is the customers are comfortable. They don't have you go in Florida at 100 degrees and they don't have to suffer with the employees because the unit is broken. That's additional saving that you cannot put a number to it. So
one of the added benefits that Walgreens has referenced for the 2010-2011 retrofits has been, to Akeem's point, the creature comfort, both for employees as well as the customers, with the drive to make sure that in areas, especially you take a worst case scenario, Puerto Rico, your Florida, that both from a dry bulb perspective and from a humidity perspective, that's controlled where it should be, in that optimal comfort zone for them. And what that in turn does is it makes sure that employees are more comfortable in their working space, so employee retention goes up. Customers are looking to spend more time in an area like a Walgreens or store like a Walgreens because they're comfortable versus being outside in Puerto Rico or Florida. So typically the greater time a customer's in there, the greater return Walgreens is seeing from that customer as far as point of sale detail.
Okay. How about any challenges you encountered in doing these replacements?
Most of the challenges, I think, was the execution part of it, because with the EMS, we had a different team, and sometimes they didn't realize or they're not familiar with the unit, what needs to be programmed, especially having the board and having programming the board to function the unit efficiently. And you mentioned about challenges. One of the worst challenges beside that, we had a lot of issues. Of course, it's not the perfect world. We have issues from employees, from managers, from one of the highest issues is permitting, and the biggest challenges for me was the permittal, because sometimes you're having a different unit with different weight. We're switching to different refrigerants. So the heavier your unit, they're required to do structural review, structural analysis to make sure everything is and it has been very, very challenging. It was more time consuming because for us, we'll define, here's a budget, you have to complete this location by this time. And the lead time especially in California, where you require for the permit, and the cost of the permit sometimes is much higher than the cost to install the units. That's one of the biggest challenges we had in the last few years.
Sure. I think dual stage wise though, John, to Akeem's point about the EMS groups, it more was a focus on making sure that they integrated into the unit, but they were not driving the unit. They were not taking over control of the function of that dual stage unit. Okay. It needed to function in its kind of closed box or black box environment. And So that was a learning process, I think, for them, but they
Yeah.
caught on pretty quickly. And I think that's one of the reasons Walgreens saw the benefit they did in 2012. It's the first time they used the dual-stage motors. And I think that's actually what's prompting a lot of the focus on moving forward, looking at what Walgreens can do better. Taking that same dollar invested into a store and to say, what else can we get out of a piece of equipment like this that will reduce maintenance time, as Hakeem has said, improve creature comfort, and obviously drive efficiencies. So SingleZone VAV is the next step that Walgreens is looking at.
Yes.
Okay. We've been talking about stores, the stores that most of us are probably familiar with. Any other types of buildings which you've been using either the two-speed or the SingleZone VAV type units on?
You were involved in those warehouses?
Yeah, there's a couple distribution centers or warehouses or cases, as Walgreens calls them, that are utilizing SingleZone VAV. Okay. Design engineers that Walgreens partners with, again, core group of design engineers. They're believers in, or they maintain the same focus that Walgreens does as far as greatest return on your investment. So they look and say, from an equipment perspective, SingleZone VAV would be a benefit in certain cases or certain locations. Okay. And there have been a couple distribution centers or warehouses that we've done work with Walgreens on where SingleZone VAV has been employed at least 50% of the units. Okay.
Any differences in the benefits or the challenges or the I guess the economics, the payback's probably different?
Payback is a little bit different. I haven't heard full details as far as what that looks like to this point on the warehouses, but we know that creature comfort, we know that the product, saleable product that Walgreens maintains in these warehouses is maintained at the level that it should be. Okay. And that's a big focus for them, especially based on the fact that Walgreens houses a lot of pharmaceutical products in there. They got to make sure it's maintained from a humidity perspective as well as a dry bulb perspective at a certain level. Okay. So SingleZone VAV has definitely helped with that.
Okay. Any parting thoughts that you want to share with our viewers on this subject, or anything else that I failed to ask you that you wanted to make sure you shared?
Well, I think we basically cover almost everything just to mention, in the last 4 years, we like I said. We changed our sourcing mind to not to look just at the initial pricing for the units, like when you bid a jobs or project, that they had the concept not look at the total cost of ownership. And because when we did the research and the study, for example, when you buy a unit, this is only 15 to 20% from the total cost of ownership. So the additional maybe, let's say the price is higher, but if it has an energy efficiency, it has a lot of, like you said, the dual stage compressors and things like other options that you may add to the units, at the end of the day will be a huge saving for us.
Well, thank you for your time today. Thanks for coming in and sharing this. I hope I'm sure it's going to be a benefit and an interest to our viewers. So
thank you for having us.
Not a problem, John. Thank you, sir.
As both Hakeem and Nirmal shared, Walgreens has been able to achieve significant energy savings and lower humidity levels by installing new rooftop units with two-speed fan control. And they're planning to start installing units with variable speed fans soon. They made the proactive decision to replace equipment that is nearing the end of its expected life, which has resulted in reduced energy use, less maintenance expense, and less equipment downtime.
Now, there are a number of publications available that provide more information on the material covered today, including a recently published engineer's newsletter. A bibliography detailing these resources is included in your handout. Additionally, past broadcasts are available on DVD at trane.com/ENL. Or join the thousands who have earned continuing education credit via the ENL On Demand courses, free of charge. Visit trane.com/continuingeducation for a complete list to satisfy credentialing requirements. Many are LEED specific. Remember to fill out a survey and let us know how we're doing. AIA members, remember to turn in your member information to your local site coordinator. Finally, please join us for the last Engineers Newsletter Live program this year when we return in fall to present variable speed chiller plant operation. Thanks for joining us today. We'll see you in fall.